Live from Earth, it's Space Radio. I'm Paul Sutter, astrophysicist at Stony Brook University and the Flatiron Institute. And for the next half hour, your agent to the stars. We have got an amazing show for you today where we have a very special guest that there's a lot of varies involved in this episode because I'm just so excited. We've got a very special guest today. Now, like any episode, whether there's a guest or not, this show lives on listener questions. We record every Thursday at 8 p.m. Eastern here at Spaceman Studios in New York City. So leave a voicemail to get yourself on the air. You can also follow along with our space cadets tuning in live from around the world, including an amusing collection of eyes. We've got Idaho, we've got Iowa, we've got Indiana, we've got Illinois, we've got Ireland. Is that all the locations in the world that start with the letter I? It just might be. We might have reached peak I, but we also have Howell, New Jersey, London, UK, Washington, D.C., Pell City, Alabama, Halifax in England, Portsmouth, England, and more tuning in live. It's so fantastic to see all the space cadets tuning in live. Now, if you want to join them and have that party every Thursday night, which I know you do, you need to go to spaceradioshow.com. Oh, Iceland. Thank you, Russell. Anyone from Iceland? Anyone? Iceland's an amazing country. I would love to go there again. And Indonesia. Okay, thank you. I'm thinking off the top of my head, folks. I'm just making it up as I go along. I missed Indonesia and Iceland. Thank you, pedantic space cadets at all, as always, which is why we love you. Now, like I promised, we have a very special guest today. Joining me today, the entire country of India. It was so off the mark on that. There's so many. Irvine. Does that count? Does anyone care about Irvine? No offense, Irvine. Let's get to our guest, Dr. Brittany Kamai. Dr. Brittany Kamai is Native Hawaiian, an astrophysicist, an athlete, an author, a mentor, an advocate for creating a better world. As an experimentalist, Dr. Kamai's research focuses on improving gravitational wave detectors with novel technology ideas. She's advancing studies of seismic and acoustic metamaterials. Can't wait to ask her more about that. On a path to improve the ground-based detectors like LIGO in the Cosmic Explorer. With increased sensitivity, we will gather deeper astrophysical observations to enable precision tests of cosmology, general relativity, and stellar evolution. Dr. Kamai, welcome to the show.
Hello.
Hey, you're not living somewhere that starts with the letter I that I totally missed, right?
No. No. No, not. Yeah, there's no way I can describe this area with an I. At the beginning of the letter. The beginning of the word.
There might be an I somewhere, but you used to live in an I. You used to live in Illinois,
Yes,
as
I
did
do.
I.
Yes.
I was a Ph.D. grad student at the University of Illinois down in Urbana-Champaign. You were up in Chicago. What were you doing in Chicago? In
Yeah.
Chi-town?
So I was at the Kavli Institute for Cosmological Physics, and we were working on building this instrument called the holometer. And the intent of the instrument was to see if we could measure any signatures from space itself that could be holographic. And so, like you, I was like, what does that even mean? And I went up there and got to build the instrument from end to end. So, like putting together the vacuum system, the electronics, the optics, sweeping the water out of the tunnel. Because, we built this at Fermilab. And so it was really awesome to like squat in an old tunnel, turn it into this new experiment, and really just see what an end-to-end project looks like, from a theorist to convincing experimentalist to building the thing and measuring things. So that's what I was up there, constantly whining about being cold because I'm from Hawaii. So I'm like, like, every group meeting, that was my update for like half the year.
I'm cold.
Yeah, and they didn't listen to me until the interferometer got cold. So like we
Yep.
actually had to get a heated blanket for the interferometer, and I was like, now
And
you're
for Dr.
listening.
Kamai.
Yes.
Was there a bonus one for you? Okay, so you
Yeah.
were like the canary in the coal mine for the sensitivity of the interferometer.
Yes. Yeah.
All right,
Like,
so you were looking for if the universe had any holographic properties. What in the world does that mean?
yeah. So when we make measurements of position, right? Like if I make position measurement in X and I make a position measurement in Y, they don't really care about each other. But if this hypothesis about holography exists, then they kind of would care about each other. So the idea would be if we make this really precise position measurement between these two dimensions, and could there be some uncertainty in that position measurement because of this constraint, then we could measure it with this really, really precise ruler. And in fact, we made two really precise rulers and stuck them as close together as possible. So that's the story. This is my one of my doggies, Jessie Rose, who loves to make cameos on like literally every YouTube thing I do. So.
I am happy to interview a dog. I would do it on
Yes.
Space Radio. And Nancy, I'm not serious, because when I say like I would love to interview blah, like she actually gets that person and interviews you. So like
Yeah.
Nancy would find a dog for me to interview. So
Nancy, we can talk. Yeah.
Okay, so you're the agent that we talked to for the
Yeah,
good
exactly.
to know.
Yeah, go through me. Yes.
So you built these very, very incredibly precise rulers. How precise are the rulers that we're talking about? Talk about some of the technology involved in the holometer, which I really want to call holometer.
Yeah. Like sometimes you do. Yeah, like so it's at the precision level of like 1,000-ish. If you took the radius of a proton, which is inside of an atom, and you go 1,000 times smaller, that's how precise we can measure length measurements. And so we made two of those at really high frequencies. So at megahertz frequencies, we can measure that. And so like the things that are in there are lasers and optics, but like the guts of the holometer is not as fancy as LIGO, which is the holometer is like 40 meters, so you can kind of like walk to the end, skateboard to the end, whatever. LIGO, that's 4 kilometers, so like 2 miles. Like you got to get in a car and you're just driving, and that's the distance these lasers will take to get to the other optics. And so the reason LIGO is so much more fancy on the inside is that when black holes smash into each other, they like to do it at the same frequencies that like Earth is doing its thing, like shaking, air motion, that type of thing. So you need fancier things within that instrument to be sensitive enough to measure things from astrophysical signals. So yeah, like the holometer has similar things, but it was like way simpler. Like way simpler than LIGO.
Like LIGO basic.
Yeah, no, totally. Like in an early incarnation, it was like they were thinking of naming it Lego LIGO, and I'm like, no. Yeah.
Yeah, scientists are not the greatest when it comes to naming things. I just gotta say, we really need some help in that area.
Yeah, and I think like holometer meant like measurer of things. It was like if you look up another definition, it's like measure of things. So that same.
Got it. So your current research, so after that, you said you're now based in the California area. Like, what are you doing out there? What are you focusing on?
Yeah, so I moved to California to work on this other instrument, LIGO, and that's the fancier version of the holometer. And I think about the future of those kinds of instruments. And so the way we move into the future is that we do these tabletop experiments. We see what the latest technology that's going on in other fields and figure out what that looks like in our field of gravitational wave instrumentation. And so that's what brought me over here is like, okay, let's work on LIGO. And I like the like futuristic stuff because it's more like creative and fun. Like it's like a different kinds of pressure. Like people are in different positions. So that's where I've been thinking lately about this world of metamaterials, which is like so cool, and trying to figure out how to bring that into how we design the future of ground-based gravitational wave instrumentation with that kind of technology.
Yeah, so what exactly is a metamaterial? Like, obviously it's better than a material, but in what way?
Yeah, so I like the part that like just really like blew my mind about this was when we go through our physics path, we like read about materials and like if light interacts with materials, it could do certain things. But in those like standard books, it said light couldn't do a certain thing, so therefore we can never make invisibility cloaks. Okay, so that was like some constraint we thought we had in physics. And then metamaterials jumped on the scene and was like, no, you can. And it like it's so cool because if you like look at it started from like a theoretical physics question, like this mathematical physics question of are these unique solutions? And it turns out it's not. And you can redesign the inside to actually still conserve like the bulk properties that you need to for physics, but on the micro scale, then you can do different things. And so that's where like the metamaterials got onto the scene where it could interact with waves in a new kind of way to achieve these things that we never thought possible. And so, of course, we're nerdy physicists and we don't leave it at light. We're like, okay, sound. What about temperature? What about seismic waves? And every wave has its own level of complexity, right? Like light goes through a vacuum, the equations are simpler. You start putting waves through soil, and now you're dealing with different things.
Right.
So, yeah, so that's where the metamaterials word comes from. And it's really, really cool.
So why do we want these kinds of metamaterials? Like LIGO is working, Virgo is working, we're seeing black holes, we're seeing neutron stars, we're seeing black holes and neutron stars. Like, why do we need to push this further? What exactly are we looking for?
Oh, yes, great question. So think about if you had like a hearing aid, right? And so if your hearing could only hear so far, then you're like, oh, I can only hear the sounds that are really close to me. But if you continue to improve the precision on that, you can go further and further out and you can see things or hear things even further. And so while we've started to measure like some, right? It's like we went from the first detection of black holes to the first detection of neutron stars to like tens of them, right? And this is still the early stages of it where we have so many questions still. It's like, where do these black holes come from? They're like way bigger than we thought. What's further and further out in our universe? So in order for us to push there, we need to improve the sensitivity of the instrument. So like making your hearing aid better and more responsive to the astrophysics by being less responsive to things here on Earth. And so when we have technology like metamaterials where we can uh, shield the detector and make it even quieter, then you'll be able to push out further. And so I'm really excited about this because then it's like we start to get into like populations, right? Like if you like what we did with galaxy surveys, it's like, cool, we could look up at the sky. Cool, we made things better. All these galaxies. Now we have piles of galaxies, and then we're doing these large scale statistics. Imagine that for a whole new sample, right? Like a whole new information messenger with black holes, like populations of them.
Statistics.
I know. Yeah, so I'm excited for
Very
that.
cool. Very
Yeah.
cool. So that's for LIGO. Tell us what the Cosmic Explorer is, where it will be, who's making it. Just what's up with the Cosmic Explorer.
Yeah, so it is right now it's in the like early stages of imagining what the next generation of instrumentation needs to be. So LIGO's like running and kicking it in the US in Washington State and Louisiana Livingston. And we have our friends around the world, Virgo, Kagra, LIGO India is gonna come online soon. But we're in that what's after that, right? When we have these things online, can we still go further? And Cosmic Explorer is one of that. It's like it's our next biggest facility that would be 10 times bigger than LIGO. So it's 40 kilometers. So that's
Yeah.
a long drive to each end station. And we're still trying to figure out where would we put it, right? So it's where are you going to put this 20 mile by 20 mile L? And like what kinds of design features do we need to think about? It's like the curvature of the earth starts becoming a problem,
Mm.
like things like this that we're working through right now. So it's thinking through what R&D needs to happen today in the next 5 to 10 years to actually have that thing running in 15, 20 years. And that'll just be rocking and rolling forever.
Got it. So what role do metamaterials play in developing something like Cosmic Explorer?
Yeah, so right now we can answer the questions of like, is that a feasible technology for seismic, like reducing seismic waves around detectors? I think after we answer those questions, we can look into acoustic metamaterials, so like even more like shielding of the optics within whatever facility we make. So we're at the stage where like what is the environment going to be doing to the detector? So what can we do to engage with the environment? That type of thing.
Got it. Got it. So, what do you see as the biggest challenges to designing something like Cosmic Explorer? You mentioned the curvature of the Earth. Is there anything that is right now is a real barrier that we really need to overcome before we can have a explorer of the cosmos?
Like the optics are going to be bigger, the suspension needs to be even fancier. Like right now LIGO takes like a 80-pound baby, like those are the optics, suspends it on this itty bitty thread and then has a super complex isolation system that reduces 10 orders of magnitude of seismic vibrations. Like
That's a lot. That's not a tenth. That's 10 orders of magnitude.
orders
That's
of
like,
magnitude.
yeah,
Yeah,
that's like
right.
10 billion.
It's like, and isn't that like the most baller move? You're just like, yeah, we'll reduce 10 orders of magnitude of noise. What? Like, that's amazing. So, I mean, like, to move Cosmic Explorer to be even more sensitive than that, then we have to start reducing those kinds of things, right? You make the optics bigger. Okay, what does that do for the suspension? Like, what does that do? Like, when you want to have more powerful lasers, how do you make that happen? So, like, there's a whole bunch of R&D in that as well. So yeah, like there's a lot of big open fun questions.
And surely
That
there's a lot of very cool technological side benefits. Like if you can build a Cosmic Explorer with all these advanced materials, are we going to have like faster internet, better color TV?
probably, yeah. But I mean, like it's wild, right? Like so CCDs, right? Like that's a bunch of astronomy nerds being like, I want to have better measurements of these things up in the sky, and now we have them in our phones all the time, right? Like I don't. At the time, I don't think they would have been like, you know what we're gonna do with this technology is that every single person's gonna have access to this.
Right.
And like even with the internet too, right? Like that's a whole another, right? Like that was a bunch of nerds being like, we're gonna smash together matter, and then boom, now we have this thing called
And
the
we
internet.
want to talk about it. Yeah.
And so I don't know. I mean, like, who knows? And maybe we need to like worry about the Earth's magnetic field at like a higher precision that would then inform other types of thing that maybe the internet will get better. Or then we have like this meta made up new internet where we're not even like using electromagnetics. I don't know,
Metanet.
whatever. Metanet, yes. Coined it first, space radio.
We got a question here from Chris Luke, one of our adorable space cadets, asking about there's been a lot of news recently about using pulsar timing arrays to detect gravitational waves, and especially gravitational wave backgrounds. Could that apply to this holography problem as well?
Ooh, yeah. So, ooh, yeah. Well, I thought the question was going to take another road. It
You can take
is.
that road too if you want. It's your interview.
I'll just drive along wherever I want. Okay, so if there is this residual noise, this is the thing. So pulsar timing arrays are gigantic detectors the size of a galaxy, right? But they don't have the same level of sensitivity as you do at detectors like LIGO or the holometer. So if you had that holographic noise in an abundance that you would measure in the pulsar timing arrays, it would really mess up a lot of other things. Like I don't think we would have the large scale structure in the same way. Like there would be so many other before we would get to that. So it's a really good question. Really, really good question of how I don't think we would see it in that. So yeah.
You don't think it's just not the right like venue for that kind of party?
Yeah. Unless it like you had to have encoded it in the early universe in some sort of way. I'm not sure.
There you go. I smell the paper cooking up.
Here we go. I'm just
Here we go.
just like writing on the side right now.
But
like,
actually, like this kind of conversation, if anyone's curious, like how research papers get started, it's usually by someone asking, like, "Hey, I wonder if this would work," and then someone says, "You know what? Maybe. No, it wouldn't. Well, maybe. Well, I don't
yeah.
know." And then like you go to the blackboard and you figure it out and you write a paper.
Yeah, and like you were like, does my friend know about that? What paper was that in? Yeah. Yeah, so I mean, like, I think there's other signatures that we can talk about that would be producing that pulsar timing arrays. So like cosmic strings, primordial black holes, like those types of things. I'm not sure. Yeah.
Infinite Monkey over here on the Space Cadets is wondering, will we ever build gravitational wave generators?
We do. All right. So if you make your fist right now, everyone,
Oh,
I'm
I'll do it.
imagining.
I'll do it with you. I'll do it with you.
Yeah. Okay. So anything that has a mass and is accelerating makes gravitational waves. So start doing this. So you are generating gravitational
I'm
waves
feeling
right now.
it. I'm feeling it.
Yes.
LIGO's picking this up right now.
Yes. So yeah, so we go to black holes because they're more massive, and then we can start to work out the numbers between like, okay, there's only like 1,000 times smaller than the radius of proton. We can kind of get there. When you any mass, the scale factor in front of it is 10 to the minus 44. So
Oh,
like
that's
it's
small.
such a that's so tiny. So the amplitude of the wave is so itty bitty when we're having our dance parties. That way we would need some like extremely sensitive detector, like unbelievable. So yeah, next time we're dancing, you can
Next time
think
we're
about
dancing, well, okay. Now we know
yes,
where gold. Now we know what the Dance Explorer is going to study in the
exactly.
future.
That's the one I'll be leading like in the future.
Done, done.
Done.
Edward Hinton is wondering. He's very curious about grav. We've been talking this whole episode about gravitational waves. What is a gravitational wave made of? Like a water
Mm,
wave is made of water molecules that are wiggling up and down or going in a circle. What is a gravitational wave made of?
yes. Okay, so to get us on this journey, like we start with space. Okay, so it's not just space up in the universe, which is great. Like the space in your room, right? There's forward and back, up and down, left and right. So that's, you got here, you're sitting somewhere as a space. And the time, like you showed up for this podcast, right? Like at some time. When we before Einstein, it was like time's doing its thing, space is doing its thing. I'm not influencing space, space is just doing a thing. And then space and time came together. They're an entity. And I am now influencing space. So like in the previous pre Einstein, pre general relativity, space and time is like a soccer game, right? Like the players are on the top, they're playing whatever. The field doesn't interact with the soccer players. But when general relativity came onto the scene, space time is dynamic. So it's like a water polo game where you have the players influencing the water and the water's influencing the players. And so now space, so bringing that into space time, right, is like now me in this room, if I'm like dancing around having my party, I'm changing like the length between things, and I'm changing the time as it's marching on. But it's so tiny that you and I are not like, whoa, distorted space. I mean, depends on what
Woo!
party you're
You never.
depends on what party you're at.
You haven't been to the parties I've been to.
Yeah, so it's this ruler of space and time. That's what's actually changing. And so when we have these fancy interferometers, these fancy rulers, it's we're responsive to a dynamic space-time. So yeah, really, really good question.
No, that's fantastic. It's like in the physics jargon we call it the metric. The
Yes.
distances between points in space and time.
Yep.
In the gravitational waves are distortions in the metric, in the fundamental distance between events. That's so
Yeah.
cool. When it comes to advanced LIGO, E-LIGO, Super LIGO, Ultra LIGO, and Cosmic Explorer, and Big Bang Observatory, and LISA,
Mhm.
and ELISA, and just all the gravitational wave astronomy that we've opened up in just the past few years of going forward, what are you most excited to see with gravitational waves?
So I want to see. Okay, so this is me being an experimentalist and then say random things, and like theorists will be like, "What are you talking about?" I want to see us measure. Like, I want us to see something really funky with the general relativity. Like, that is the thing that I'm like waiting for. Is that like we start to measure like all of these black hole mergers, and then there's like some weird stuff happening in the ring downs. We're like, oh, what's that? And then we start to measure a whole bunch of them further out, and it's like we're making these like kinds of measurements that you see like large scale structure measurements but of black holes, and then it's something different, right? Like we have this tension right now with like CMB and like like
The
local
supernova
universe.
stuff. Yeah.
Yeah, supernova, and it's like, oh, this is tension, and then I want like I want LIGO to like come in there, measure all these black holes, and there's something else, you know.
You want to prove Einstein wrong.
I want to add, like,
You,
really, we're in a weird spot, right? Like, think
yeah.
about it, right? Like, what is dark energy? We're all just kind of like, that's cool, that's part of the universe, but it's like, what? So I like want these
Who
other,
asked for that?
you know, I want these other clues that's going to lead us on a new path. So that's what I'm really excited about, of having a different kind of messenger from astrophysics.
Speaking of the fantastic answer, I would love to finally find a crack in general relativity and see what's going on. But see, speaking of messenger, you are both an author and an advocate, and you were among the leaders, if not the primary leader, of the shutdown STEM movement.
Yeah.
Last June. So, can you talk about what that movement was, what instigated it, and what's been going on since June?
Oh, yeah. So okay, 2020, we're going
Complicated year.
complicated year. You know, we're still living in like another version of it. So, like, we're going through this global pandemic, you know, and on top of that, you know, we go through this extreme national crisis on race, right? All of these people are losing their lives at the hands of the state that's not being held accountable, right? And we see people in the streets demonstrating amidst a pandemic. Like, that's how much our whole entire country is like, oh my gosh, we can't be doing this, right? And we watched like different industries respond to this, right? Like the professional sports leagues, like the women's national, like the women's basketball, like there's so many like athletes saying Black Lives Matter, and we need to center that. And all of these people can't be, like, this can't be going on, right? And so you watch an industry like the music industry, like they came up with like a Blackout Tuesday, and the question is, where's science, right? Like in this perpetuation of systemic racism, what are we doing to eradicate it, right? This anti-Black racism that's pervasive through our culture, what are we doing about it? And so that's like the seed of it. And then the seed of it was reaching out to other leaders that I've known my path through astrophysics. And we saw these letters come through from institutions being like, we stand in solidarity with you. And it's like, do you?
Do you really?
There's been
Nice letter. It's because it's easy to write a letter. It's easy to have a sentiment.
Yeah. And so then it was a reflection and accountability of what are you going to do? What is the systemic change that we're going to be making, right? How are we going to eradicate this anti-Black racism that is in all of us, right? And if we're not conscious about it, we're going to continue to embed that in everything, right? Like if you think about science, right? The internet, our phone, like this computer, like all of this is science, but scientists are just like, no, man, we're just over here doing other things. It's like,
And
no,
scientists, yeah.
yeah. And so it was bringing that together and saying like, what, like, get together, right? Like wherever you are on this, like if you are in pain because that is your demographic of people and you're hurting and you need a break, take a break, heal, find the community that you need. For the rest of you, if you haven't been thinking about it or actively doing work, you need to read, take action, and come up with a plan. And so that's what really was at the core of it. And the leaders who were part of this brought that in there, right? It was like everyone can be part of this. No matter where you are on the globe, like the US impacts you in science, right? Like just think about that. Like how many institutions are in the US? How many like research collaborations are we part of, right? Like you're influenced by this. So it was amazing to see so many other people activate their own leadership to say, in my space, what am I going to do, right? Me individually, my groups, my role, like editors from Nature were just like, we got to do something, like, and it was just like everybody in different tiers were just kind of like, okay, I can do something and let me figure something out. And so that's what really was so powerful, was that so many people said, yes, we need to transform. So it was a day, it's not shutting down STEM for all eternity. It was a day to transform. And so we're still seeing like ripple effects from it. Like we had like the American Physical Society just said at the end of last year that they're going to incorporate police conduct when choosing a conference site. they bring in millions of dollars to cities
Oh yeah.
every single year, right? And so it's like these kinds of like changes all over the place. It's really it's there's a lot of hope that we can
Yeah.
transform. Yeah.
Absolutely. And it takes like even tiny incremental change is still change. It's still progress, and we'll do whatever we can. How can people follow you? You're a very interesting person. You're wonderful to chat to with. How can people find you online and follow your professional work, the shutdown STEM, all of that, what you're associated with?
Oh yeah. I think so follow going to brittanykamai.com, I do my best to try to aggregate everything there. I'm on Twitter a lot, so that's Cosmo Jellyfish. I'm also on Instagram. I'm still kind of new with Instagram.
Aren't
Yeah,
we
so I
all?
think like there's such different platforms, you know? I'm like, okay, I think I got it with Twitter, and then it's like this is a new game.
Yep.
So yeah, Cosmo Jellyfish and BrittanyKamai.com, and you'll find it. And shutdownstem.com will be up. There's so many resources. Like engage if you missed June 10th, 2020, turns out you could still get to work. So there's a
You
lot of
can still
opportunities.
transform. It's
Yeah.
like shutdown STEM is now transform STEM,
Yeah, yeah,
and it
yes,
never stops.
exactly. It never
Very
stops.
cool.
Yes.
Dr. Kamai, thank you so much for joining us this evening. It's been wonderful to chat with you, and best of luck.
Thank you so much. Thank you for this opportunity. Take care.
Absolutely. All right, Space Cadets, that was a really fun interview. I enjoyed that. I hope you did too. Unfortunately, we don't have a cheese tonight. We don't have a cheese tonight. I know you're as disappointed as I am. The shop was closed. We couldn't get the cheese. It's okay. It's okay. This Dom's Cheese is always a great supporter of this show. We will be back next week with more cheese. Speaking of support, you can support this show by going to patreon.com/pmsutter. And if you'd like to contribute and follow along and help with the efforts to transform STEM, to make it more aware of and this is something I talk about in my upcoming book, A Sickness in Science, where scientists want to close themselves off from humanity. Scientists want to close themselves off from society and pretend that we can just do science in a bubble, in a vacuum. That's impossible. That's a lie. It's always been a lie. And something we really need to address. Scientists are a part of society. We are human beings. We are enmeshed in our culture. And it's not just about diversity, even though that's a major issue. That is a symptom of much larger breakdowns in how science operates, and that'll be in my book. It's coming up. I just finished the draft. It's in the editing phase right now with my publisher, and when it comes out, we're gonna have a lot of discussions about it. Trust me. Just like we have discussions about my current book, How to Die in Space, which you can buy autographed copies off my website, pmsutter.com/store. And go check out shutdownstem.com, brittanykamai.com. Follow her on Cosmo Jellyfish. That is just so funny. And yes, Visto 2D, science can never be separated from people or cheese. That's once again, thank you for joining me on this voyage of space radio. Once again, I'm Paul Sutter. The show is brought to you by you. Go to patreon.com/pmsutter to keep supporting the show. You can also drop a super chat over in the YouTube comments live anytime you want. Thank you, Nancy Graziano, for producing the show and wrangling the Space Cadets, and also arranging our wonderful guests that we have the privilege to interview. Catch the live stream every Thursday at 8 p.m. Eastern. Visit spaceradioshow.com for more info, links to the live stream locations, and the episode archive. You can follow me on social media if you feel like it. It's at Paul Matt Sutter. Thanks again, Space Cadets, for listening. See you next week. And remember, science is for sharing. End of transmission.